Okay, we're going to continue here in chapter 5. So last time we started talking about some important sort of conversions. We talked about Avogadro's number. Remember, Avogadro's number is 1 mole pretty much of anything is 6.022 times 10 to the 23. And remember, the units here can be different things, atoms or molecules. And again, really, Avogadro's number is our conversion factor that allows us to go from moles to atoms or molecules and back and forth. The other really important sort of guy that we use is molar mass. And molar mass has units of grams per mole. It is basically taken from the periodic table, all the bottom numbers, which are the atomic mass, but equivalent sort of number for the molar mass. We also can use it as a conversion factor. Basically, you could do grams over moles or moles over grams, depending on sort of the calculation that you're doing. We typically go 4 significant figures when we do take it off the periodic table for our values here. And again, that is the most important one that takes us, again, through this conversion back and forth. We also saw that we could use a chemical formula to really, as a conversion factor as well. So I think maybe we had something like this, maybe. And again, if we were not, for example, interested in the entire thing, but maybe we're interested in just, say, one of the elements that are involved, either the carbon, the hydrogen, or the oxygen, we could actually use the bottom numbers here as the moles of each of these guys. And we can come up with several relationships. We could say 1 mole of the entire thing here gives us 2 moles of carbon. We could say 1 mole of the entire thing gives us 6 moles of hydrogen, and 1 mole of the entire thing there will get us 1 mole of oxygen. So by using really the subscripts here in the chemical formula as the moles, it allows us to come up with a mole-to-mole relationship, and again, kind of go from the whole thing to an individual element, which at that point you could find how many atoms that may be. You could find how many grams that may be of that particular element that is involved. Any questions on any of that there? Okay, so continuing on here, the next thing we're going to talk about is percent composition by mass. So percent composition by mass basically is we take the mass of each individual element in a formula, and we divide it by the molar mass of the entire formula and times it by 100. So for example, here, if we were going to do our guy here, C2H6O, we could get the molar mass of the whole thing here, which is 4607 grams per mole, which we did previously. And we can figure out the percentages of each of the elements that are here by taking the mass of each one. So in this particular formula, there are 2 carbons. So we can take 2 times the mass of a carbon from a periodic table, which is 1201, divided by the molar mass of the entire compound, which is 4607 times 100%. And for carbon, by mass, we would see 2 times 12.01 divided by 4607 times 100, not 1,000, about 52.14%. So about 52.14% carbon. We could do the same thing for our hydrogen. The percentage of hydrogen in this formula, since there's 6 of them, would be 6 times 1.008 grams per mole from the periodic table, divided by the molar mass of the entire compound, which is 4607 grams per mole. Once again, times it by 100%, and that would get you 6 times 1.008 divided by 4607 times 100, about 13%, we'll call it. So by mass here, this compound is made up of about 13% hydrogen, 52% carbon. And we could finally do it for oxygen here, which would be 16 grams per mole since there's just one oxygen, divided by our 4607 times 100%. And in this case here, we would end up with about 3473. Now, obviously, at this point, we maybe didn't need to do the oxygen. We could have added up those two, right, and subtracted from 100, and that would have gave us the percentage of oxygen that was there. Obviously, when we add up all of the percentages here, they should be approximately 100%, and they are in this case. Obviously, if you have more than 100, way more than 100%, then something probably went wrong. So by mass, this is basically mostly carbon, followed by oxygen, and hydrogen being the third percentage there. Any questions on how to calculate percent composition by mass there for each element? So this is something that's used a lot when we try to find like the empirical formula. So a lot of times you are given sort of the percent composition by mass of each of the elements in a compound. And what we're going to talk about next is actually how to go about solving for empirical formulas. So a reminder that there's two types of formulas that we come across here. We kind of did in the experiment last week. We have the empirical formula, and we have really the molecular formula. The empirical formula is always the simplest whole number ratio of what elements are present. While the molecular formula tells you exactly how many of each element are present. So for example, if we have a molecular formula of C4H8, that is basically 4 carbons for every 8 hydrogens. That's also the same ratio as basically 1 carbon for every 2 hydrogens, which means if we wanted the empirical formula for this guy, it would basically be CH2 would be the empirical formula for that guy. So it's always the simplest whole number ratio of what's present. Now, sometimes the molecular formula and the empirical formula are going to be the same. So if you had something like water, which is obviously the molecular formula, water is obviously 2 hydrogens for every 1 oxygen that's present, although it looks like a 10, but 1 oxygen that's present. And you obviously cannot get any lower than that and still have whole numbers. So that is both the molecular formula and the empirical formula here. So sometimes it is the same thing for a particular compound. All ionic compounds are always empirical formulas. So all ionic compounds, our formulas, are really empirical formulas. So when we do put them together, we always put them together again in the simplest way that gets us to 0. Although we could put it together like Ca2F4, which is still balanced, but is not the simplest thing. We would reduce this down to the proper formula over here. So when we do ionic compounds and ionic formulas, they are always really the empirical formula. Obviously in lab, like we did last week, through simple experimentation, you can calculate the empirical formula by figuring out how much of one element you started with and how much of the other element kind of came on for the ride. Like we did the tin we started with, right? And we threw some oxygen on at the end, and we started with silver and we threw some chlorine on at the end. And by knowing the masses, you could calculate sort of the empirical formula. So let's talk about the steps though to calculate an empirical formula here in a sort of textbook problem and the steps that you should follow. So to calculate the empirical formula, there's a few steps that you do follow. The first step is if you are given the percent composition by mass, which is very commonly done, you can assume that you have 100 grams of it and basically turn the percentages into grams. So whatever sort of units they give you, the different amounts of each element present, you really do want to get them to grams, because the next thing that you want to do is convert your grams to moles. And again, that is going to be the molar mass from the periodic table, right? That's going to allow you to do that. At this point, you will have moles of each element present. So for example, you then would divide by the smallest number of moles. So once again, if we had, say, 2 moles of A and 10 moles of B, when we got to this step, we would divide everybody by 2 moles of A, basically. That would give us 1 for this guy. That would give us 5 for this guy. And if you divide it at this point by the smallest number of moles, and you pretty much hit a whole number, either exactly a whole number or like, 0.99 or really, really super close to a whole number, or just a hair over a whole number, maybe like 0.01 or 0.03 or something like that. That basically will get you your empirical formula. So in this case, this would be our empirical formula. Now, if you go through and you do divide and you really don't get a whole number and really don't get close to a whole number, so for example, if we had something like 2 moles of A and 5 moles, we'll do that one, 5 moles of B. When we would divide by 2 moles here in this situation, we would get 1 and we would get 2.5, which means our empirical formula would be A1, B2.5. The subscripts, which are the moles of each of these elements, they do need to be whole numbers. So 2.5 is a little too far to round, and pretty much a textbook problem. Anything outside of the laboratory is kind of too far to round. So what we typically do is just a trial by error to try to find a factor to multiply that number by that will get us a whole number. So in this case, we could do, obviously, 2 would get us a whole number. We then would actually multiply that empirical formula by 2, not just the B in this case, but both of them in this case. And that would give us the proper empirical formula of A2B5 in this case. So typical endings in sort of textbook problems and stuff like that, where you would not round, is, you got like a 0.25, maybe a 0.5, a 0.33, those type of endings are kind of too far to round. So really in textbook problems, it does have to be almost like on it. And the only difference is maybe a slight rounding that you did in the calculation that you just missed it by. But if it's sort of any of those sort of endings, you got to kind of find a factor to multiply it by to get it to a whole number. Now, unlike the lab that we did, typically in sort of laboratory experiments, since it is a lab and stuff like that, in experiment, we do typically round a little bit more than you typically would do in sort of a textbook type problem. But definitely in a textbook problem, you should do a lot of rounding unless it's really close. Any questions on any of that there? All right. So why don't we try one here? We got percent composition here of potassium, which is 24.75. We have Mn, which is 34.77%, and oxygen, which is 40.51. Why don't you calculate the empirical formula? I'll give you some numbers that might be helpful. Potassium is 3910. Oxygen is 16. And Mn is something, 54, 53, I think. 54, 54, I guess. 54, 94, maybe. I think it was 54, 94. Give or take a few. 54, 94. All right, so follow those steps there, see what the empirical formula you come up with here. Good look, see how you're doing. So first off, when you're given the percent composition by mass, it's a good idea to quickly kind of look at the percentages and just make sure you got 100% when you add them together. In this case, we do got about 100%, are pretty darn close to 100%. May not always, again, be a perfect 100%, maybe a little bit over, a little bit less, but it should definitely be in that ballpark. Obviously, if you do not have 100%, you are missing some element, and there's probably some way to figure out what's missing and how much of it. Since we do have 100% here, we can assume 100 grams. And really the purpose of assuming 100 grams is just to keep the numbers the same. You could assume whatever number you want, but then the numbers change. So if we assume 100 grams, that means that basically for potassium, we have 24.75 grams of potassium. For Mn, there we would have, start with the number, maybe 34.77 grams of Mn. And for oxygen there, we would have 40.51 grams of oxygen. So after we kind of get them into grams, the next thing that we really want to do is convert everybody into moles. So we're going to use the molar mass from the periodic table, obviously, to do so. All right, so for potassium there, that's 3910 will go on the bottom. Moles will go up on top. For the Mn, that will be 5494 grams on the bottom. Moles up on top. And for the oxygen, that will be 16 grams on the bottom and moles up there on top. So if we do that, converting those guys into moles, 2475 divided by 3910 gets us about, we'll call it 0.633, 0.6330 moles. If we do our Mn, also about 0.633, we'll call it as well. Basically, I will go 29, pretty close. And oxygen here, 40.51 divided by 16, 2.532 moles. Any questions up to that point? At this point, we're going to divide by the smallest number, which in this case is either one of those two, 0.63s basically. So we're going to divide this guy by 0.6329. We'll divide this guy by 0.6329. And we'll divide this guy by 0.6329. That obviously gives us 1 for everybody there. Figured out something right. So that gives us 1 for this guy, 1 for that guy, and I believe about 4 for that guy. And at that point, we pretty much hit whole numbers. So that would be our empirical formula, KMnO4, a little potassium permanganate. Any questions on any of those steps? Okay, so that is a very common way at which we can calculate the empirical formula. There's also another sort of process that's sometimes used to calculate the empirical formula, and that is what is known as combustion analysis. And combustion analysis is basically a combustion reaction, which you might be familiar with. It's like what happens when you light the Bunsen burner. You take something that's organic, pretty much, which is basically carbon, hydrogens, and oxygen, and you throw it through a combustion reaction with a little bit of O2, probably some heat, and you will get out always CO2, carbon dioxide, and water will be produced in this particular case. Now, by knowing in this process, or when you do this type of analysis, we actually have some collectors of the CO2 and the water. So you'll know how many grams of CO2 that you collected. You'll know how many grams of water that you collected in the original analysis here. And from that information, we could actually get how many grams of carbon originally started with. And from that information from the water, we could actually get how many grams of the hydrogen we originally started with. As in this particular experiment, the only thing that has carbon and hydrogen is our original sort of unknown sample. So our organic sort of unknown guy would be the guy that would provide all the carbon and all the hydrogen that would get in there. Could we use the CO2 and the water to figure out how much oxygen was in the original guy? In this analysis, we could not, because we actually added oxygen, right? So some of that oxygen got into each of those, so we would not be able to sort of figure out directly from the water or the CO2 really how much oxygen we collected. But what we can do is, once we kind of do a little calculation to figure out how many grams of carbon there was and how many grams of hydrogen there was, we could take the grams of the original sample, which basically had carbon, hydrogen, and oxygen, and we could subtract out the mass of that from the grams of carbon that was collected, the grams of hydrogen that was collected. And by subtracting that out, that then would tell us how many grams of oxygen came from the original sort of compound. So we have to do a little bit of work here in this type of empirical formula problem up front to figure out how many grams of carbon there is, how many grams of hydrogen, and how many grams of oxygen there is. At the point where you get all three of those grams, then you basically roll into an empirical formula problem. You convert them into moles, you divide by the smallest number of moles, but it's just kind of a little bit of work up front to get to those numbers so that you could kind of do the empirical formula sort of process. So let's go through one here together to see how one of these works. So we have some ethanol, and ethanol is our organic compound here. It basically contains carbon, hydrogen, and oxygen. We have our water absorber here. We have our carbon dioxide absorber here. We're feeding some oxygen into this reaction. And if we did this sort of reaction and we started with 11.5 grams of ethanol, and we were able to collect 22 grams of CO2 and 13.5 grams of water, we want to really know what is the empirical formula here of ethanol. So as I mentioned before, the CO2 is really going to be our source of carbon that was in the original compound. So we have CO2, but we're really interested in just the carbon part. So this is where we can use the formula as a conversion factor. And for every 1 mole of CO2, how many moles of carbon is there? There is 1 mole of carbon. So kind of like what we did in those previous problems. The water here, again, is our source of hydrogen. And we're not interested in the whole thing. We're just interested in the hydrogen part. So once again, we could use the formula to say for every 1 mole of water, we get 2 moles of hydrogen. Any questions on that there? So these are obviously a mole-to-mole relationship, which means probably the first thing I need to do with my CO2 and water is convert it into moles. So we need to convert it into moles. So we will need the molar mass of CO2 and water. So CO2 is 12.01 grams per mole plus 2 times 16 for the oxygens. And roughly go with 44.01 grams per mole. Hopefully. And we want to do water as well. So water's molar mass, we got 2 hydrogens at 1.008 grams per mole and oxygen at 16 grams per mole. That is something like 18.02 grams per mole. So obviously we get that from the periodic table. We're going to use that as a conversion factor to convert these guys into moles. So starting with our CO2, we got 22 grams of CO2 using the molar mass from the periodic table. Grams go on the bottom, 44.01 grams per mole of CO2. My grams cancel. And at this point, I'm in moles of CO2, which means I could actually use my conversion here to get me to carbon. And if I do that for every 1 mole of CO2 from the equation, I get 1 mole of carbon. I'm actually going to get a number here because I'm thinking forward here about what I got to do next. So that is going to give me 0. We'll call it 4999 moles of carbon. I then can convert the carbon moles into grams by using the molar mass of just carbon here. So 12.01 grams per mole of carbon. And that gets me roughly 6. We'll call it 00 grams of carbon. So basically from that CO2 was collected, 6 grams of the 11.5 grams we started with was the carbon, basically. We could do the exact same calculation for the water. So if we do the exact same one here for the water, we're going to start with our 13.5 grams of water that was collected. We're going to convert it into moles by using the molar mass of water. And once again here, we're interested in just the hydrogen. So we're going to use our relationship for hydrogen to water to get us to moles of hydrogen. So 1 mole of water is 2 moles of hydrogen. Once again here, I'm going to get the answer here for moles. So 13.5 times 2 divided by 18.02 gets us 1.498, we'll call it, moles of hydrogen. And once again, using the molar mass of just hydrogen here from the periodic table, we could figure out how many grams that was. So the moles will cancel. And that would get us 1.510, looks like, maybe. Any questions so far on that calculation there? At this point, I've now figured out how many grams of hydrogen came from the original sample, which is about 1 gram or so. How many grams of carbon, which is about 6 grams, which means I can now find the oxygen by adding those together basically and subtracting from our original sample. So our original sample was 11.5 grams, and that basically contained carbon, hydrogen, and oxygen. So if I subtract the mass of the carbon and I subtract the mass there of the hydrogen, that will tell me how much oxygen was in the original sample. And that would be, in this case, about 3.99 grams, we'll call it. Any questions on that there? So from this analysis, I was able to determine the grams of carbon, the grams of hydrogen, and the grams of oxygen that came from the original sort of unknown sample. Any questions on any part of it? Now I can pretty much do my empirical formula problem. So now I'm going to take these grams, convert them to moles, which is why I actually got the moles already, so I don't have to do those calculations again. So I already have my moles of carbon. I got my moles of hydrogen here, which is why I got the answer. So we'll get our moles of oxygen, which would be 16 grams per mole. And that would get us 0.249, 0.249 moles of oxygen. So now I have all 3 of my moles. And now I just need to divide by the smallest, which looks like it is this guy here. So we'll take the 0.4999 moles of carbon divided by 0.249. We'll take our 1.498 moles of hydrogen divided by 0.249, and we'll take our 0.249 moles of oxygen, and divided by 0.249. That obviously gives us 1 for the guy in the middle. Gives us approximately 6, about 6.01. So it's close enough to 6 in that case. And here 0.4999 divided by 0.249 gets us 2. So in this case, we did hit all whole numbers. So our empirical formula here would be C2H6NO. Any questions on any of those steps? So this type of analysis, when you're doing empirical formula, pretty much is a little bit of work at the front, and then you kind of roll into the empirical formula. The goal here is, again, just to get the grams of all 3 of those things. This typically only works for organic type of compounds that contain carbon, hydrogen, oxygen. Obviously, if you had more elements, it would be much harder to figure out the 4th element or something like that. So really just carbon, hydrogen, oxygen, organic type bias. Any questions on any of those steps there? Yeah. There's a much prettier move of it. Hopefully they end up with the same. Pretty close. There we go. Hey, we got the right answer. Good deal. All right, let's then talk about how we determine the molecular formula. So when determining the molecular formula, you pretty much need 3 things to allow you to calculate it. You need the empirical formula. So either it will be given to you in the problem, or you've got to go through the steps we just did and calculate the empirical formula, either through combustion analysis or regular empirical formula sort of calculation. Once you have the empirical formula, the other thing that you need is the molar mass of the empirical formula. And lastly, you need really the molar mass of the compound. And that could be the apparent molar mass of the compound. The good news is this is typically given to you in the problem. So somewhere in the problem, they'll say, hey, this thing has a molar mass of like 80 grams per mole. They may even give you a range, like it has a mass that ranges from like 90 to 100 grams or something like that. But somewhere in the problem, they'll give you pretty much the molar mass of the compound. So what you do is you take the molar mass of the compound that they give you. You take the molar mass of your empirical formula that you probably calculate, and it will give you a number. And this number is what you multiply the empirical formula by. So if we had an empirical formula of A2B5, and we did this little move here, and it said a 4, we basically would multiply everything here by 4, and it would be A8B20 would be our molecular formula. So the one place where it's pretty acceptable to round, even if it's a little past being really close to the cutoff, is here, because this number really should be a whole number multiple. So, you know, if you happen to get something like 6.2, that's probably close enough for 6 or something like that in this situation. So when you do this sort of calculation here, really should give you a whole number, but sometimes, you know, it may not be a perfect whole number. So it's okay to kind of round at that point, because really, again, the molecular formula and the empirical formula are related to each other by really a whole number multiple, right? They reduce down. So let's take a look at one here. Let's calculate both the empirical and molecular formula, or the molecular formula here. You might need to do the empirical. Okay, let's take a look since we're getting to the end here. In this particular case, we do want to calculate the molecular formula, which basically needs 3 things. We need the empirical formula, which was not given to us, so we do need to calculate it. We obviously would then need the molar mass of the empirical formula, which we could calculate. And thirdly, we need the molar mass of the compound, and that was given to us. And again, it's an approximate value of about 30 grams per mole. So we do have the 30 grams per mole, which is the molar mass of the approximate molar mass of the compound. So the first thing we're going to do is very much just roll through an empirical formula calculation, 6.44 grams, one more 4. A boron, we're going to convert it into moles. That'll be 10.81 grams per mole of boron. We're going to do the same thing with hydrogen, 1.08 18.803 grams of hydrogen, 1.008 grams per mole of hydrogen. So that will get us our 6.444 divided by 10.81 gets us 0.5961 moles of boron, and for our hydrogen 1.7886, we'll call it R7 moles of hydrogen. In this case, we're going to divide by boron, which is the smaller number there. So everybody's going to get divided by our boron. That gives us 1 for this guy, and I believe maybe 3 for that guy. 3 for that guy. So since we hit whole numbers, that would be our empirical formula. BH3 would be our empirical formula. We need the molar mass of this guy, so that would be 10.81 grams per mole plus 3 times 1.008 grams per mole. Gets us about 13. .834 grams per mole. That's the empirical formula of molar mass. So what we do is we take the approximate molar mass that was given to us, which is 30. We divide it by 13.834. And in this case, we end up with something like 2.17. So again, in this case, at this step, it is safe to round to the nearest whole number because it should be pretty much a whole number multiple of it. And this is an approximate molar mass, so it's not the exact molar mass, so it won't be perfect. So we're going to take that factor of 2 basically and multiply our empirical formula by it, which would give us B2H6 for our molecular formula here. Any questions on that one there? All right, we're laid up there for now.